Imagine a single, isolated subatomic particle traveling freely in a perfectly straight line through the empty vacuum of space. The moment it crosses an invisible boundary into a magnetic field, its path violently whips into a continuous, perfectly flat circle. If another particle enters on a slight slant, it doesn't form a flat circle. Instead, it's forced into a spiraling, three-dimensional corkscrew shape, pushing forward. The magnetic field dictates these exact, mathematically perfect geometric paths without actually speeding the particles up or slowing them down. How does an invisible field do that? In standard Newtonian mechanics, when a force pushes an object, it transfers kinetic energy to that object and changes its speed. In physics, we refer to this transfer of energy as doing work. In the late 19th century, Dutch physicist Hendrik Lorentz formulated the precise equations that govern how charged particles interact with these fields. His mathematical laws reveal a strange paradox. The magnetic component of the Lorentz force is incredibly strong, yet it transfers absolutely zero kinetic energy to the moving particle. This diagram shows why. Look at the particle's velocity vector and the magnetic force. They are locked at exactly 90 degrees. Because the force pushes purely sideways, never forward or backward, it is impossible to alter the particle's speed. Stripped of the ability to change how fast the particle moves, the magnetic force does the only thing it can. It constantly pulls the particle's direction inward, trapping it in orbit. Let's look at the simplest scenario: a particle hitting a uniform magnetic field head-on at a perfect right angle. This top-down diagram shows the uniform field as an array of crosses. The sideways magnetic force pulls the particle toward a central point, acting exactly like the tension on a tetherball to steer the charge into a perfect circle. We map this by balancing centripetal force against magnetic force. Solving for the radius reveals the geometry. R equals mv over qb. A faster particle carries more momentum, demanding a wider turn, but increasing the magnetic field forces a tighter ring. The radius of the particle's orbit is simply the physical manifestation of its momentum fighting against the grip of the magnetic field. In reality, particles rarely strike a magnetic field perfectly head-on. So what happens when they enter at an arbitrary, non-perpendicular angle? This diagram shows the result. The flat circle stretches out, tracing a spiraling three-dimensional corkscrew path called a helix. To understand why, physicists split the particle's slanted velocity into two tracks, perpendicular and parallel to the field. The perpendicular component feels the full sideways magnetic force, creating the circular spinning motion. The parallel component points directly along the field lines. Experiencing zero magnetic force, it coasts forward at a constant speed. Combine them. A constant spin, layered over a steady drift, creates the helix. Physicists measure this specific forward drift using a term called pitch. Pitch is simply the linear distance the particle travels straight along the field lines during the time it takes to complete exactly one rotation. Any angled entry creates this helix. It is the perfect physical compromise between total magnetic capture and unhindered forward momentum. This brings us to a highly significant mathematical anomaly found in the angular frequency equation. Angular frequency is a measure of how many rotations a particle completes in a given amount of time. Notice the variables here: charge, magnetic field, and mass. The variable for the particle's velocity is completely missing from the formula. This means a fast particle screaming around a massive circle and a slow particle lazily drifting in a tiny circle will both complete their rotations in perfect synchronization. The time to complete a lap is totally independent of the particle's speed or energy. This fixed, predictable rhythm is the core principle that allows us to control them. Scientists exploited this unchanging rhythm to build the very first massive particle accelerators, known as cyclotrons. A cyclotron is a powerful machine that spirals charged particles outward to accelerate them to incredibly high energies. Looking at this early cyclotron hardware, you can see the sheer scale of the electromagnets required to produce the fields needed to contain these particles. Because the orbital timing never fluctuates, engineers can pulse a separate electric field at that exact frequency. This creates a perfectly timed electrical kick that accelerates the particle twice per orbit. The responsibilities are split. The electric field does the actual work of speeding the particle up, while the massive magnetic field simply steers the widening, high-speed path. Magnetic fields change direction, they never speed. By understanding this perpendicular paradox, we have gained the power to steer the building blocks of the universe.